In section 8.7, we're going to look at how do we graph radical functions. We just spent a lesson in 8.6 on simplifying radical expressions, so we're just going to kind of continue this theme and look at what the graphs of these type of functions might look like. And we'll also talk about domain and range of these functions as well. Well, as we've seen in the past, whenever we encounter new functions, I like to draw what I call, again, the parent function, which is just kind of the most basic square root function that we can have. It's just square root of x. There's nothing else added or subtracted or multiplied or anything like that. So let's begin with just a table of values. Notice I'm being quite selective with my x values that I choose. If you start thinking ahead, you'll understand why. Plugging in these numbers in for x, and I'm taking the square root of those numbers. So the square root of 0 is 0. Plug in the 1, the square root of 1 is 1. Substitute in the 4, the square root of 4 is 2. Substitute in the 9, the square root of 9 is 3. Notice there are no negatives in this table, because we can't square root the negative number. We can if we want imaginary numbers, but we don't want imaginary numbers. They wouldn't appear on our graph. So I don't need negatives. I can just start at 0 and go positive from there. So my points are 0, 0, 1, 1, 4, 2, 9, 3. It looks like that. It only continues to the right forever. It does not continue past 0, 0. Cannot come to the left where the negative x's are. Again, there are no negative x's. Now, as far as domain and range goes, let's just do that real quick. Domain and range of this function as it's drawn, the most basic function, domain is 0 to infinity. Range is 0 to infinity. And domain is the x's, and the x's start right here at 0 and they go to positive infinity. The range is the y's, starts right here at 0 and goes out to infinity, going up to infinity. The only other radical function we're going to look at in this section is the cubic function. The only other radical function we're going to look at in this section is the cube root function. So again, the parent function for that. And for this one, I'm going to choose 0, 1, 8. The cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. And unlike square roots, we can cube root negatives. So the cube root of -1, -1, the cube root of -8 is -2. We get points that look like this. Hold on, that one's in the wrong spot. Out here. Kind of like this. The domain of this function is negative infinity to positive infinity. It goes left and right forever without exception. The range of this function is also negative infinity to positive infinity. It goes down forever, goes up forever. This will always be the domain and range for a cube root function. Doesn't matter where this cube root function is. I could move it up here and it would have the exact same domain and range. It's always going to go left and right. It's always going to go down and up without fail. So always will be a domain and range for a cube root function. Alright, let's graph a square root function that is a little more complex than the parent function that we started with. I'm going to make a table of values to do this. With a square root function, the first thing I like to do is find the smallest x value. And typically I can do that by just taking what's inside the square root, setting it equal to 0, and solving it for x. The smallest x value I can have is 3. If I choose any x value smaller than 3, say 2, and put in for the x, well, that makes the square root of a negative number, which I can't do. This ensures that I find the smallest value that would not result then in a negative under the square root. So I start with 3. Okay, so plug in for x. 3 minus 3 makes 0. Square root of 0 is 0, and 0 times 2 is still 0. Okay, I might try the next number after 3, 4. 4 minus 3 is 1. Square root of 1 is 1. 2 times 1 is 2. Okay, now I'm going to skip to 7. Notice I'm trying to build this like the parent function. I'm going to skip to a number that, when substituted for x here, makes a perfect square under the square root. 7 minus 3 is 4. Square root of 4 is 2. 2 times that 2 is 4. So I've got point at 3, 0, 4, 2, 7, 4, it looks like that. Domain. Well, this one starts at 3 and goes to infinity. Starts at 3 on the x. Range starts at 0, 0 on the y, and goes up to infinity. With a cube root function, I'm going to do similar to what I did with the square root function. I'm going to make a table of values. Unlike the last one where I tried to find the smallest x value, here I kind of find maybe the center x value. I don't know, maybe that's a decent way to say it. But I'm going to take this right here, set it equal to 0. That's 4. I'm going to start right there. 4 in for x makes this be 0. Cube root of 0 is 0. 3 times 0 is 0. So we have the point 4, 0. Now, I know that I can take the cube root of 1 and the cube root of negative 1. So I kind of ask myself, what values for x would make x minus 4 be 1? That would be 5. 5 minus 4 makes 1, which cube roots to 1 times 3 is 3. What value for x makes negative 1? And that would be 3. 3 minus 4 makes negative 1, which cube roots to negative 1 times 3 is negative 3. Okay, now I know I can cube root 8, and I can cube root negative 8. So what value for x makes 8? And that would be 12. 12 minus 4 is 8. Cube roots to 2 times the 3 is 6. So 12, we're up here at 6, where we're kind of off the graph a little bit. How about making negative 8? What number for x, so that x minus 4 makes negative 8? That would be negative 4. That makes negative 8, which cube roots to negative 2 times 3 is negative 6. And here's my points. For this particular function, domain and range are both, again, because it's cube root, they're always negative infinity to positive infinity. How about we end with an inequality? This could be done with a cube root or a square root. I chose simply a square root. Again, you can make a table of values. Smallest number I could put in for x would be, about y there. The smallest number I can put in for x would be 0. Square root of 0 is 0 plus 4 is 4. I try 1. Square root of 1 is 1 plus 4 is 5. Next I'm going to skip to 4 because the square root of 4 is 2. 2 plus 4 is 6. Next I'm going to skip to 9. Square root of 9 is 3 plus 4 is 7. Okay, hopefully that wasn't too fast. Alright, now recall when we do inequalities, we always connect the points with either a dotted, dashed, or a solid line. This one, because the inequality is not equal to, I'll make it a dashed line. And then we have to shade either above or below this line. The inequality is less than implies below the line. So we're going to now shade below, keeping conscious of the fact that this graph does not go past the y-axis. So we cannot shade down in this empty area.